Session preview. My name is Limin Jia. I'm a research professor at EC at Carnegie Mellon University. Because it's a very broad topic, so I'll start with quotes from various areas. So the first quote is from Ross Anderson. He's a prominent security researcher. He says security is about building systems to remain dependable in the face of malice, error, or mischance. And then US Air Force states that security is ensuring systems operating properly and remain secure from outside intrusion. And finally, we have Palo Alto Networks. On its webpage, it says security is a set of techniques used to protect the integrity of an organization's security architecture and safeguard its data against attack, damages, or unauthorized accesses. So I would like to call out that when you think about security, you have to think about attackers. That's the highlighted red parts of all these statements. You also typically have to think about the properties, what you are trying to achieve. What's so interesting about security is that there's no black and white. There's no one-size-fits-all. So you really have to consider many aspects when you answer the question, how do I build a secure system? Is my system secure? You will have to ask yourself, what is your target system? Who are the attackers, the adversaries? What are the security requirements or guarantees you're aiming for? And what are the approaches you're aiming for, considering all the other aspects? All right, so I'm going to highlight these four. So it's really, from a programming language perspective, we are very good at coming up with abstractions, modeling, and analysis techniques. So in this session, we have 3 papers. I list the title on the right-hand side. And I'm going to talk about, for each paper, what is their target system, adversary, secure guarantees, and we typically skip the approaches because of time. So let's jump to paper 1. So paper 1 is in the area of memory safety. And the system we're talking about is essentially programs or processes. So on the right, I have an example of a buggy C program. And here, the adversary is someone who can provide inputs and execute the program. So here, let's assume the attacker calls this buggy function and give the input, which is a very long string of A's. So to illustrate the problem here is I draw out the memory layout of this function when it executes. Because there's so many A's, the A will just keep copying. It will override, corrupt everything after the buffer. And in particular, it's going to override something called the function return address. So as a result, this program would actually crash instead of returning to the caller. So this is a standard buffer overrun problem. When we look at security guarantees, it's kind of saying, what's the guarantee we want to rule out this class of problems? So the guarantee we're considering here is memory safety, meaning no out-of-bound access, no point debuffing, so on and so forth. We also care about control flow integrity. So here you want your program to follow intended semantics, not here crash, or even start remote shell controlled by the attacker. For this one, I'll go into a little bit more detail about approaches. It's very relevant to paper 1. So as language designer, your first choice is we should use a language or push them to use language that don't expose pointers to developers at all. Right? We have many languages in this category. Or if we want to be practical, we want to expose pointers, but we want to expose only the well-behaved ones. So one toolset we have is type systems. So we can, for example, use linear or affine types to precisely track pointers so that the type system can reason about what's safe, what's unsafe. That's what Rust is taking. So that's why Rust is advertising memory safety. You can also use dependent types to reason about the bounds of your buffer. So your compiler is going to throw out programs that actually have out-of-bounds access. I'm going to skip the rest of the type stuff. I think it's a very interesting topic. So in addition to types, you can also leverage runtime. You want to have your language runtime to keep track of pointer information so that when there is out-of-bound access at runtime, the runtime system is going to kill the program and abort before the attacker do more damage. So many academic projects and also real systems take that approach as well. Going back to this no one-size-fits-all topic, I want to mention that if you have one defense mechanism that can provide one security property, it doesn't mean that it works for another. So for example, here, I have a mechanism that can confine attacker to a region in this green box. If the attacker tries to access memory in another region, in a different green box, this mechanism will stop it. However, if I care about the attacker to not screw up subdivisions in this green box, my first approach will not work. I actually need something else to actually do this. Right? So this is roughly what paper 1 is about. It's about how do I improve this WebAssembly language. It's already provides some notion of memory safety, but now if I want to provide even stronger guarantees, what should I do about this? All right, that's paper 1. Now paper 2 is a different topic. I have 3 minutes to cover 2 papers. So this is about information flow security. So here, what we have is a system that computes on input, produce outputs. We have public and secret inputs and outputs. Here, I have an attacker essentially can provide public inputs, observe public outputs. Again, there are different kinds of attackers. Sometimes the attacker can observe progress or termination or timing information. So in this little example, I have login website. You put in password. You have add script on the page. You really don't want your add script know your password. Right? That's the guarantee we want to have. At the high level, we want to make sure the secret information does not leak to the attackers. I'm going to skip the approaches. So now the question is, how do we specify this guarantee I want that secret information cannot leak to the attackers? The standard thing to do is for me to define non-interference, essentially saying that the secret cannot interfere with the attacker's observation. There are lots of literature behind this, so if you're interested, you should look into that. Now, being on the practical side again, non-interference would make sure there's no information from secret to public. This is too strict. Typically, your system would have to have some amount of declassification. So in the login page, the attacker always knows the password it tried is the correct one or not. So instead, here, if we actually want some amount of controlled flow, now coming back to the guarantee specification question, how can we specify a security guarantee under declassification? We need to have a way of quantifying precisely how much information is being leaked to the attacker. So that's what paper 2 is about. It's actually a theoretical foundation to quantify precisely how much information is being leaked. All right, probably have 1 minute for the last one. It's going to be a short one. So again, we're going to switch a different application domain. We're actually looking at remote communications. You can imagine this is Alice and Bob chatting with each other over WhatsApp, over a untrusted network. Here, your attacker is sitting in the network. We typically call them an active network attacker. It can eavesdrop on messages, intercept send messages, but we assume it cannot break crypto. And in terms of security guarantee, the security goals here, there are many different goals. You may want to keep your communication secret. You might want to authenticate user. You might actually try to do key exchange here. So obviously, the approach here, you're trying to design a protocol so that you can use encryption, signing, and so on to realize your security goal. So now, again, we'll come back to the question of how do we specify the security goal and security guarantees. So one method is trace-based. This is used by various protocol verification tools, analysis tools like ProVerif and Tamarin, where I can say that what I want is that if I look at any possible execution trace, including the attacker have no way of knowing what is the secret key they're trying to exchange. Or I can do something called simulation-based. That's taken by the universal composability side. Essentially, what I'm trying to say is that my protocol is secure because it's no less secure than the idea of functionality, which is defined to be secure. Right? So there are a whole bunch of math and formalism behind this. So this is what paper 3 is about. Paper 3 is talking about how can we use language technique to model protocols in such a way so that I can easily verify and reason about simulation-based security guarantees in protocols. All right, this is the end of it. So this is the paper. This is the session. Please come to the security session to take questions.
I think we have time for one question as we sort of swap speakers. Yes. One quick question from anyone? Okay, thank you.